In this video, we continue with chapter 3.3 about properties of determinants. And so now we are going to see how we can find the determinant of the transpose of a matrix. So we're going to start with theorem 3.9, which has a long proof. So that says if A is a square matrix, then the determinant of A transpose is equal to the determinant of A. So for our proof, we're going to start with A is a square matrix of order n. And then we know from section 2.4 that A can be factored into lower and upper triangular decomposition. So it can be factored as matrix P times A equals LDU, where P is a permutation matrix, L is a lower triangular matrix with all the ones on the main diagonal, D is a diagonal matrix, and U is the upper triangular with all the ones on the main diagonal. All right, so you might remember back in section 2.4, we said not every matrix has a Lu decomposition, but every matrix does have what's known as this Ldu decomposition. So D is a diagonal matrix that does row swaps that we might need. So you can think about the fact that this applies to every square matrix of order n. So L is obtained from the identity matrix by adding a multiple of the rows containing the diagonal ones to the rows below the diagonal. So we know the determinant of matrix L equals the determinant of the identity, which is 1 by theorem 3.3b. Likewise, matrix U is obtained from the identity matrix by adding a multiple of the rows containing the diagonal ones to the rows above the diagonal. So the determinant of matrix U also is the same as the determinant of the identity, which is 1 by that same theorem 3.3b. And then by theorem 3.2, we know the determinant of a diagonal matrix is just a product of the values on the diagonal. So we could say the determinant of matrix D is the product of all its diagonal elements. All right, this matrix P is a product of elementary row swap matrices. So this lets us swap the rows we might need before we do the Lu decomposition. So this is what makes any square matrix able to be in a Lu decomposition if we have this matrix P multiplied by A first to swap the rows. And so each of these row swap matrices has each row swap has a determinant of -1. So the determinant of the whole matrix P is the product of some numbers of -1. So if the number of row swaps was even, the determinant of P is going to be a 1. And if the number of row swaps is odd, the determinant of P is going to be a -1. All right, so let's let E be a bunch of row matrices, n by 1 matrices, and we can form them by I'm sorry, these are a bunch of column matrices. Then we're going to transpose them to make row matrices. And we'll put those together to form this row swap matrix P. So we've got E to the I1 transpose, E to the I2 transpose, et cetera, where we form these different rows of matrices with ones in them to make P the row swap matrix. So remember, if you're swapping rows, you just need ones in different places to multiply it out and swap which row is where. You don't need to have any constants there. So then we can think about, well, P could be transposed into just a transpose of that matrix. So we call it each column matrix now because we had the transposes in P. So P transpose is going to be the same values, these E columns. And then P times P transpose gives us this matrix here, which is E transpose from each row of matrix P multiplied by the elements E from P transpose. And so the whole point in doing this is, well, we know these products are all going to be 1 or 0. So we get our 1s on the diagonal because we've got the diagonal elements there. You can see these are EI2 transpose and EI2. So if you think about E2, this is like 1, 0, ... 0. And then if you're multiplying by the transpose, that's 0, 1, 0, dot, 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 0, like this. So this is going to give you a 1. If you think about multiplying instead values where the ones are in different positions, like if you multiplied, this is say EI2 transpose, if you multiply that by EI1, then you're going to end up with a 0 because the ones are in different positions. So that's why we get 1s on all the diagonals and 0s everywhere else. So you can see to get a 1, you have to have EI2 transpose multiplied by EI2, EI3 transpose multiplied by EI3. So if you've got something where your dimensions are different, like here, well, the 0s and the 1s don't line up, so you end up with a 0 there. So when we multiply this matrix P by its transpose, we get the identity matrix, and we know the determinant of the identity matrix is 1. So then that tells us either determinant of matrix P is 1, so the determinant of P transpose is 1, or the determinant of matrix P is -1, so the determinant of matrix P transpose is -1. Either way, they're equal. All right, so we have, going back to our square matrix A, we have this relationship that matrix P times matrix A, where P is this row swap, gives us the LDU factorization, where L is our lower matrix, U is our upper triangular matrix, and D is a diagonal matrix. So we know then by products of determinants that the determinant product of determinant P times determinant A equals the determinant product of determinant L times determinant U times determinant D. Sorry, LDU, I said it in the wrong order. And we know determinant of P is going to be 1 or -1. Then on the other side, we know determinant of L is 1, determinant of U is 1, and so we're just left with determinant D. So then we have this relationship, determinant P multiplied by determinant A equals determinant D, and then we can rearrange that to get this right here. The determinant A equals determinant D divided by determinant P. Ooh. All right, so now we take the transpose and we end up with a similar relationship. We know D is diagonal, so determinant, well, D transpose equals D, so the determinants are, of course, equal. L transpose is going to be an upper triangular matrix, so the determinant is still 1. And then U transpose is a lower triangular matrix, and so that determinant is still 1. So then we have the same relationship that the determinant of A transpose equals determinant of the diagonal divided by determinant of P transpose, but determinant of P transpose just equals determinant of P from up here. So determinant of A transpose equals determinant of A. All right, let's look at an example. So here is matrix A, and let's go into SIMPy and verify the determinant of A is equal to the determinant of its transpose. So I'll clear out SIMPy. So matrix A here is a 4x4 matrix. So we've got 6, 5, 1, and -1. And anytime you have a 4x4 matrix, be good to yourself and let technology help you. Unless you've got a nice setup with a lot of zeros in a row, you don't want to go through that calculation by hand with the cofactors. All right, let's verify type matrix A-OK with no errors. Looks good. And then we are checking A transpose. So that's A dot T in SIMPy. There's A transpose. And then we want to just check their determinants. The determinant of A, we can type DET and put A in parentheses. And then determinant of A transpose, we can type DET, determinant A dot T. Voila, the same result. And it makes some sense just based on the symmetry. If you think about trying to set these up with cofactors and choosing values, you would do it in a very symmetric way. So when you get to the, reduced forms where you've got zeros and ones, those are going to be symmetric and all the elements are symmetric. So it makes total sense that the determinant values that you're calculating would end up being just the exact same values. Okay, so in chapter 3.4, which we will do in the next week, we are going to see some applications of how we can use determinants in some problem solving scenarios. And for this week, you are going to practice these properties of determinants in the group discussion and in the lab assignment.